Hello everyone, and welcome back to another video where we are going to be evaluating the incomplete gamma function for some integer, well I suppose in this case it is n plus 1, but it also would work for just n. This is a part of a larger integral that I was doing, and I'm making this sort of video on the side just to speed up the upcoming video so that we don't spend like 10 minutes or however long this video will be evaluating this. So without further ado, let's get started, shall we? The way we're going to approach this is actually kind of similar to how you might evaluate the normal gamma function. Namely, we're going to use integration by parts first. So what we're going to do is actually start by integrating e to the minus t, and then we're going to end up differentiating the t to the n term. So what I mean by that, so this integral right here is equal to x to the n, or minus x to the n, times e to the minus x, and then minus the integral from 0 to x of n t to the n minus 1 times e to the minus t dt. But remember, there's an extra minus sign here, so that actually becomes a plus. So to evaluate this next integral, what we're going to do is effectively the same thing. We're going to integrate this bit right here and differentiate that bit via integration by parts. So doing that, we find that we have minus x to the n minus 1, or pardon me, minus nx to the n minus 1 times e to the minus t, and then plus the integral from 0 to x of n times n minus 1 times t to the n minus 2 times e to the minus t dt. And you'll see here that the pattern actually really does just repeat itself. So let's kind of see where this leads. In total, what we're going to have then is minus x to the n e to the minus x minus n x to the n minus 1 e to the minus t, and then minus n minus 1 x to the n minus 2, and then e to the minus t, and then so on and so forth until we get to, well, what are we going to get to? Well, the most we can go to, since we're assuming that n is indeed some integer, or I should specify some positive integer, the most we can subtract from our x term right here is going to be, well, n itself. And what happens when we get that? Well, we're going to have an e to the minus t term, sure. Or I do apologize, I am mixing up the notation here. No. Those should all be x's. But what we're going to have in the end is, whenever we get to like the last integration by parts bit, is e to the minus x, that part's not going to change. But what we're going to have with these terms right here, the n's and our x's, is, well, we're going to end up having this little term right here, this 2, whatever we're subtracting, end up being n. And we're going to be multiplying n times n minus 1, and then times n minus 2, all the way down to just, well, n minus n plus 1, which is just going to be 1, right? And that right there is just a factorial. We know that. So the term that's going to be following this e to the minus x is just going to be an n factorial. But that's not the full story, actually, because you'll see here that we're integrating from, well, x to 0. And in every single case throughout this, we've had something to plug in for x, yes, but whenever we try to plug in, say, 0, right? That right there is just going to be 0 by virtue of there's a big ol' x out front. But whenever we get to this point right here, that's not the case at all. And I should specify that this is a minus e to the minus x times n factorial. But whenever we get to the end, if we plug in 0, there's no x to make that whole term go to 0. So we're left with something that is non-zero. And as a result, what we have is just, well, this right here. So this term right here, it's going to be plus, and then, well, e to the 0, which is just 1, times n factorial. So this right here is our formula in general for the incomplete gamma function, or the lower incomplete gamma function, more specifically. But this is awfully ugly, I think we can all agree, because we have, well, some dot dot dots, and it's really not too formal. So let's really try to clean this up a bit. So you might see two things that we can factor out from here. One being this n factorial right here, but also all these e to the minus x terms. So let's do that real fast. That leaves us with n factorial times 1 minus e to the minus x, but then times this very long polynomial, which is just going to be x to the n over n factorial, because remember we're factoring the n factorial out, and then plus x to the n minus 1 over n factorial. But what exactly is n over n factorial? Well, that right there is just going to be n minus 1 factorial, so we can just rewrite it as that. And the trend for this is just going to continue. So we're going to have plus dot dot dot, x to the n minus some j over n minus j factorial. And then, of course, all the way down to just 1. But we still have these sort of inconvenient dot dot dots. We have these ellipses. So let's try to formalize this slightly more by, well, making this right here just a sum. We can express this as the sum from, say, we can use this right here, j equals 0 to n of x to the n minus j divided by n minus j factorial. And we might spot check a couple of terms, say, okay, let's plug in, j equals 0, and you'll see we end up with this term right here, our 0th term. And then you might say, okay, let's plug in j is equal to n, and you'll see that we end up with our 1 term right here, and you do that for all them in between, you'll see that it works. But that also does look a little bit weird. We have just n minus j, and since our summation index is actually going up to n, starting at 0, what we can actually do is this curious little thing, and say this is actually just a sum from j equals 0 to n still, but of just x to the j over j factorial. Which might seem a little bit weird at first, but this just comes from the fact that, well, it doesn't matter which order, in this case, we're adding these in, they're all going to get added anyway. So instead of adding them from, say, this direction, with this summation, we're actually adding them in the opposite direction. So with all of this in hand, we can now rewrite our lower incomplete gamma function, lots of adjectives there, as the following. N factorial times 1 minus e to the minus x times the sum from j equals 0 to n of x to the j over j factorial. And that right there is just the formula for the lower incomplete gamma function, which we can just write as gamma of n plus 1 comma x. So I hope you all enjoyed this video, and I also hope myself that the video in which this is used will be out soon. But in the meantime, hope all y'all are doing well, and I will see you in the next one. Bye!